So now let's see what compositions are going to do. After we find inverses, then we had a lot of fun just composing functions together. So, if I just have two functions, let's see, f of x, we'll do something that you're going to really like. So x squared plus 2, and g of x is equal to x minus 5. These are two functions separate from each other. Now, a lot of times we're going to have like functions inside of functions, and these are called compositions. It's like building one function in terms of another. So you remember the notation f of g of x. So this actually means that I'm taking the g function, this whole g function, and sticking it inside to the f function. So I start with all my x values of the f function, like this. I just write my f function, but I don't put any variables in it. So f is I take my variable and square it, and then I add 2 to it. But what am I really plugging into the f function? The g function. So that's just going to be stuck right inside there. I'm going to compose the two together. So now, this is your favorite part, right? When you square it, what do you have to do? I can't hear you. Oh, right. FOIL. Don't forget about the middle term, okay? So we get x squared minus 5x plus 25 plus 2. So when you simplify that stuff all together, x squared minus 10x plus 27 would be your composition. There you go. And then it's kind of fun too because I could do it the opposite direction. I could take g and compose the g function with the f function. And at first you guys all thought it was going to end up being the same thing, but then after you did like 500, you realize, oh, it's actually going to be different. So now I start with the g function. I just take the whatever variable I have here, I stick giant parentheses there, and then subtract 5. So what goes into the g function? The f function. So here we go. Now this one's a lot easier to simplify. Not as much fun algebraically. So g of f of x would just be equal to x squared minus 3. So that brings us to what happens. That was fun, you know, the building blocks for what happens when you compose two inverses together. So then, if I said, oh, here you have g of x and its inverse, a really cool thing happens. So if I compose g with its inverse, let's call this f of x. Let's say you don't know they're really inverses, like we just found 2 seconds ago. Let's do this. G of f of x. So that means I'm going to start with the g function. That's that giant square root thing. I'm going to put some variable in there and subtract 5. So what goes in there? Oh yeah, the f function. Okay, so x squared plus 5. Now I just simplify. So first the 5's are canceling out, and then I get the square root of x squared, which is just going to give me x. Oh yeah, okay, cool. Well, what happens if I did it the other way, f of g of x? I don't know. So let's start with the the f function, square it, add 5, but now in this case, I'm going to plug in the original g of x. Oh my gosh, this is cool. Do you guys see what's going to happen? When you square the square root, it goes away, so x minus 5 plus 5. Oh my gosh, the 5 cancels out again. And look what you get! The same thing. They're the same. So that's a cool thing about compositions with inverse functions. If you have f composed with f inverse of x, you will always get the same thing, x. Or if you have f inverse composed with f of x, you will always get the same thing, x. So that's like a cool little inversey thing. So the last topic that we have today were translations. So those were things that we talked about a lot last year in Algebra 3-4, moving left, moving right, shifting up, shifting down. We talked about that a lot with the trig functions, graphing those. So let's see if we can remember some stuff. So let's say now I'm going to start off with the basic function of x cubed. So if I did something like x cubed plus 3, do you remember that this meant that I shifted everything up 3? Took that same exact function, I didn't change the shape of it or anything, I just moved everything up 3. And then if I did x cubed minus 2, that meant that I moved everything down 2. Now nothing changed, the shape of this didn't change, it's exactly the same, it's just moving down. Now if you wanted to move left or right, that meant that you needed parentheses for that operation. So something's going to happen inside the parentheses, like x minus 1. So shifting it on the inside here, if this is minus, this means it's going to move to the right one. And then if you have like x plus 2 cubed, then it moves left 2. Now all of these translations, they don't change the shape at all. It just takes the regular cubic graph, moves it right, moves it left. No shape change. So if I took this, y is equal to, let's say, x plus 5 cubed minus 3, then what's happening with my cubic graph is I'm moving it left 5 and down 3. So if I think about the basic cubic graph, looks like that, goes through that important origin. I could just take this and say, well, I'll just move that point left 5, down 3. Look at that awesome scale. And then I just do the same exact graph like that. And that's a good enough sketch for us for just practicing these things. And then you had things that like stretched out functions vertically or horizontally or shrunk them. And that happens when you start multiplying. So remember we talked about this in Algebra 3-4 a lot too. If I have this basic function x squared, and then I take some number and multiply it like 2x squared. Remember this number here would make the parabola skinnier. Or if I multiplied it by a number like a fraction, 1/3 x squared, that made it wider. So these multipliers actually change the shape of the graph. They'll still have the same general, curve and everything, but this one will be wider and this one will be a lot narrower, but they will still look like parabolas. So then we said, okay, let's get a little bit abstract about it. What happens if I have just some weird function that we started graphing just little pieces of things? So let's say I had something that looks like this, like a semicircle right here, so maybe this is -3, 0, and this is 0, 3, and then, so a little quarter part of a circle right there, and then maybe just a line segment right there to 4, 0. And I'm going to say, here's my function right here, f of x. Now I want to take it and move it all around. So let's say now I want to take my function and do 2 times f of x plus 7 minus 3. So what is this transformation doing to this weird shape right here? So that's when we used mapping to see what was going on. So everything that happens to x happens inside the parentheses. So I know by looking at that, if I think back to over here, this is taking all my values and moving it all left 7. So what's going on there is you're moving it left 7. This right here is making it go down 3. And this thing on the outside was a vertical stretch of 2. Oops. Times 2. So Nothing's going to change in the horizontal direction except that you're moving everything to the left 7. We're going to double the height of this, and we're going to move it down 3. So if you can imagine, we're just taking the shape, moving it left, moving it down, but then stretching it in this direction. What's going to happen to these points? Well, let's see. If I was going to move this to the left 7, the new coordinates would be -10, 0. So what's happening to all the x values is I'm taking all the x values and moving each one individually left 7. Always opposite. Remember, whatever was happening here to the x values, you had to do exactly the opposite. And then for the y values, what's happening? Well, then y happened directly. So we thought of this whole thing as all being y. So you would take 2 times your y value, that's what stretches it, and then subtract 3 from it, that's what makes it move down. So then we would say, okay, this point -3, 0, I'm going to send it through the mapping, and once it comes out of that mapping, let's see, -3 minus 7, so the x value is moving to -10, and then the y value is moving to -3. So that's where this point's going to get moved to. Then we would do the next one. So 0, 3. That's going to be moved to -7. 2 times 3 is 6. Minus 3 is 3. Whoops. Positive 3. And then the final one, 4, 0. 4 minus 7 is -3. That's totally wrong. And then 0 times 2 is 0 minus 3 is -3. So if I put those back on the graph in a different color, maybe you can see what the mapping is going to do. So, not really to scale, but -10, -3, maybe it's going to be over here. -7, +3, well that's the same thing, so it should be up there. -7, maybe over here. And then -3, -3. So I connect this with the same kind of circular piece, and then this with the line. So see, everything moved left 7, down 3, but it's stretched by 2 vertically, but this distance is still the same between the x values, because all we did to x was just move it left. Day 1 review, check. Yay, now do your homework. Have fun. Don't forget your unit circle.